Click the link in the description to download your own copy of this video's problem. Hey guys, Russ here coming with a fantastic chemistry video, and today we're going to look at adding HBr across a pi bond or a carbon-carbon double bond. Now this one is a little challenging because it's asymmetrical. Now adding a HBr to a symmetrical alkene is not a big deal. We've seen examples of that. Now we're going to add it to a unsymmetrical alkene. So now there's a choice. Where does the bromine go? Draw the mechanisms to show each product. Predict which product will form. Be sure to refer to your mechanism in your explanation. Not a problem. This is a classic question in organic chemistry. Classic. You see this all the time. This is Markovnikov addition, essentially. Markovnikov addition says that the proton will go to the least substituted carbon and the nucleophile will go to the most substituted carbon. Something like that is what Markovnikov's rule says. The reason I don't know it off by heart is because I don't like to memorize rules. What I'd rather do is know why things happen. So I'm going to explain to you why Markovnikov's rule works so you don't have to memorize it. You already know why it works. You already know about cation stability because we've already studied it. We've already done lots of videos on it. So it's all about cation stability. Let's see what let me show you what I mean. Let me show you what I mean. So let's start over here. Let's start right here. So there, let me draw that again. So there is our alkene. Now this is hydrogen bromide. This is not hydrobromic acid, hydrogen bromide. How do I know? There's no water. If there was water here, this would be hydrobromic acid. HBr by itself, no solvent, is hydrogen bromide. So keep that in mind. It's very important. Okay, now at this point, the pi bond will deprotonate HBr. There we go. So the proton deprotonates. Now at this point, the proton has a choice. Let me show you what I mean by choice. There's two different carbocation intermediates that you could potentially draw from here. Let me draw the first one. You could put the carbocation here and the hydrogen here. You could do that. That's just putting the hydrogen on one of the carbons. Okay, there's a carbon here it could go to. There's a carbon here it could go to. It can go to either one. We can predict which one it will go to, though. So I'll put the carbocation there and the hydrogen here. Well, now, if you read Markovnikov's rule, you'll see it says very clearly that the hydrogen that you're adding goes to the least substituted carbon. Doesn't say why, though. Here's why. Here's the least substituted carbon right here. So the hydrogen went there. This is the one we're going to form. We're actually not going to form this one. That one's not going to form. This one it will, however, because if the hydrogen goes to the carbon with the least substitution, it forms the most substituted carbocation. And you guys all know that the more substituted a carbocation is, the more stable it is, the more quickly it will form. So this is a lower energy carbocation. It will form in preference to the higher energy secondary carbocation. This is secondary. This is tertiary. Tertiary carbocations are much more stable. You guys already know that. So there's no need to belabor this point. So what happens next? The bromide, because there's no other nucleophile in this reaction, the bromide attacks the carbocation, forming the product. And it's all because of Markovnikov's rule, which is all because of cation stability, which you already know all about carbocation stability. So you're not really learning anything new. All you're really learning is a new application of what you've already learned. All right, guys? So I hope you found this video helpful. If you did, slap that like button, leave a comment down below, and subscribe to my channel. It really is helpful to me in my endeavors to grow this channel, to reach the whole world, to teach them organic chemistry. And if you could, please Share my content with your family and friends or anyone that you know is struggling with organic chemistry. Maybe I can help them out. And with that, I want to wish you all good luck and good chemistry. We'll see you soon. Email drbetts@protonmail.com if you would like a copy of every problem in this series.